Hi, welcome to our pre-recorded material for InterPore 2021 poster session. Here, we'd like to give you a quick glimpse at Meshless Lattice Boltzmann Method applied to calculations of fluid flow in porous media. The main motivation for the presented work was the fact that the voids in porous samples form very complex geometries. What follows is that direct in vivo measurements of, for example, velocity fields of flows inside such samples is most often impossible. Further, even using popular numerical methods like finite volume or finite differences to solve hydrodynamic equations at pore scale is still a challenging task, mostly because of the need to discretize pore spaces with a mesh. But what if one gives up mesh discretization and chooses so-called meshless approach instead? Here we go. Meshless methods do not require any information on connectivity between the nodes discretizing the problem. In the presented algorithm, a meshless method called radial basis functions interpolation is used. The core idea behind it is to represent some multidimensional function as a linear combination of a finite number of radial functions. The latter maps the mentioned multidimensional space into a set of scalars in a way that the function's value at some point x depends only on Euclidean distance between this point and so-called function's center x0. Examples of such functions vary from non-smooth cubic RBFs to C-infinity class Gaussian bells. In real life, we're faced with radial functions in the form of point gravitational field or intensity of music playing from a speaker. So, going back to linear combination, it could be viewed as a whole orchestra of RBFs playing at various volumes to give you a classical arrangement of your favorite rock piece. Okay, but let's leave gigs for Friday evenings and take a closer look at history and features of RBF interpolation. Its beginnings can be traced back to early 1970s when Hardy represented a piece of terrain geometry with RBF interpolant, similarly as one would represent a two-argument function with, say, polynomials rising from its two-dimensional Taylor expansion. Since then, this approach has been widely studied and utilized to a vast diversity of problems, not only as an interpolation tool, but also as a mean of numerical differentiation. Its main upsides, compared to other methods, are truly meshless nature. One operates on scattered, non-connected node sets with no restrictions on their layout density. Secondly, multidimensionality, when d-dimensional vectors are transformed into simple scalars, which is great for interpolating data dependent on a large number of variables that one has to deal with, for example, in machine learning. And lastly, ease of implementation, when changing interpolation bases and parameters is often a matter of rewriting a few lines of code, for example, including distance in the additional dimension when extending the problem from 2D to 3D. What's just been said sounds like a good choice for dealing with highly complex geometries of porous media, where due to space-varying flow properties, local discretization refinement will come in hand. Thus, let's see how to incorporate RBF interpolation into standard lattice Boltzmann methods and what new possibilities such a fusion has to offer. The main idea of meshless semi-Lagrangian LBM, presented by Lin and his co-workers in 2019, is to give up square lattice for physical space discretization and operate on RBF-specific scattered non-connected points, called Eulerian points. Then, the collision step is performed in each of them in a pretty the same way as in usual LBM. However, at this point, post-collision distribution function is interpolated with the previously discussed scheme from the Eulerian points to Lagrangian points, whose coordinates correspond to the distances traveled by particle populations in the subsequent streaming step. In this way, one gets boundary-fitted variable density discretization difficult to achieve in standard LBM, with velocity and physical space discretizations decoupled. To check if the described algorithm presents an opportunity for producing accurate results of porous media flow, we calculated tortuosities and permeabilities of randomly generated geometries and compared their dependence on porosity with 1999 work by Koponen and his co-workers. At high porosities, the results match each other very well. The reason for their disagreement at low porosity regime may be the size of obstacles inserted into the flow and geometry inhomogeneity due to that. Well, to sum things up, we present the meshless version of Lattice Boltzmann method, which may offer significant improvements compared to the standard approach, which are especially useful in simulations of flow in porous media. Although the idea of augmenting LBM with any kind of interpolation is not new, as to our best knowledge, it's never been used for tackling this type of flows with truly irregular discretization. The presented results suggest a big potential lying in the method, with low porosity disagreements stemming possibly from the domain geometry itself rather than the solver's flaws. We'll gladly welcome your questions and criticism during the live session on the 2nd of June. Also, be sure to vote for the poster you liked the most at the conference contest. See you back soon!